That leads us to the next anti-aging 8, protein restriction. Reducing protein intake would seem to be a more feasible lifelong strategy than serious long-term caloric restriction, but the relative contribution of protein restriction to the overall longevity benefits of caloric restriction is controversial. In insects, the life extension from restricting overall food intake appears to be wholly a protein reduction phenomenon, but in mammals the data appear to be mixed. There's a body of evidence that suggests that protein restriction alone accounts for approximately half of the life-extending effects of caloric restriction. A 20% average increase in maximum lifespan of rodents compared to about 40% with caloric restriction. At the same time, there are rodent studies showing lifespan extension with dietary restriction that appears independent of protein intake, nearly identical longevity from cutting food intake by 40% whether or not protein intake is held steady. More recently, the pendulum has swung in the other direction, suggesting that all of the lifespan benefits of caloric restriction derive from the drop in protein intake. In this chapter, I'll explore how we can account for these discrepancies and what implications this has for human longevity. FGF21. In the year 2000, a new human hormone was discovered. It was the 21st documented fibroblast growth factor, so it was named FGF21. Since its discovery, it has emerged as a key agent for promotion of metabolic and artery health, leanness, and longevity. Inject FGF21 into fat monkeys, and they lose body weight without reducing food intake, and not just a little, a 27% drop in body fat, eating the same amount. In mice, it increases their lifespan by 30 to 40%, comparable to lifelong caloric restriction, but achieved without decreasing food intake. FGF21 appears to act through multiple aging pathways, boosting AMPK and sirtuin activity, while inhibiting IGF-1 and mTOR signaling. The thought that FGF21 could potentially be used as a hormone therapy to extend lifespan got Big Pharma salivating, raising the question, can aging be drugged? The idea that one drug could treat obesity, diabetes, and hypertension all the while slowing aging might have seemed impossible, but suddenly became a tantalizing prospect. And the reason you can't just give people straight FGF21 is it gets rapidly broken down the body, so you'd have to get injection every hour or two around the clock. So drug companies started to patent a variety of longer-acting FGF21 lookalikes, and indeed, giving people some PF05231023, they can lose about 10 pounds in 25 days, along with dramatic drops in triglycerides and cholesterol. But then the side effects of these newfangled drugs started cropping up. What about packaging the FGF21 gene into a virus, then injecting the virus and having it stitch extra FGF21 genes into your DNA? Or you can just lace up your running shoes. Exercise and fasting to boost FGF21. Exercise boosts FGF21 levels, which may in fact be one of the reasons it's so good for us. Circulating FGF21 rises immediately after a bout of exercise, peaking an hour afterwards and returning to baseline within 3 hours. Which works better though, aerobic exercise, 8 weeks of running training, or resistance exercise, 8 weeks of lifting weights? The answer is both. But the resistance exercise edged out the running, a 42% increase in FGF21 versus a 25% increase, respectively. What can we do with diet? Rather than gene editing or injections, wouldn't it be easier to just stimulate our own endogenous natural production through diet? One way is through no diet at all. FGF21 is known as both the pro-longevity hormone and the starvation hormone. Fasting induces FGF21, but not just a day or two without food. Unlike mice, who show an increase after only 6 hours of fasting, humans don't get a notable surge in FGF21 until after a week. Fasting can quadruple FGF21, but that takes 10 days of fasting, which is the very poster child of an unsustainable eating pattern. How to boost FGF21 with diet. How can we get the benefits of fasting without the starvation? Might a ketogenic diet be able to mimic the fast? In rodents, keto diets raise FGF21 levels, but in people, they don't work. In fact, FGF21 levels may drop by 40% after 1 to 3 months on a ketogenic diet. High-fat diets may even interfere with the boost you get from exercise, as demonstrated in a 12-week study of high-intensity interval training. Thankfully, the starvation hormone, characterized as a quote-unquote systemic enhancer of longevity, can be raised with less drastic measures than a prolonged fast. by eating more carbs and less protein. Even without reducing protein intake, FGF21 levels shoot up when people are fed a lot of starchy foods. The healthiest source would likely be legumes and intact whole grains. FGF21 is bumped up by butyrate. The short-chain fatty acids are good gut flora make from fiber, as well as the starch-blocking drug acarbose, at least in mice. This suggests slow-digesting starches, such as pasta, beans, and intact grains, could have a similar pro-longevity effect. Circulating FGF21 levels are also, quote-unquote, rapidly and robustly induced by dietary protein restriction. Researchers saw more than 150% increase in FGF21 within 4 weeks, even in the context of overeating calories. And the quote-unquote protein restriction was just restricting protein intake from the typical excess that most Americans get down close to the recommended amount. The recommended dietary allowance for protein is around 50 grams a day, 46 grams for women, 56 grams for men. The researchers took men who were averaging twice that, 112 grams, which is about the average of what many American men get, and randomized them down to 64 grams of protein a day. So the quote-unquote protein-restricted group was still getting more than enough protein. Do that, and you can essentially double FGF21 levels in your blood within about 6 weeks. That may help explain why, despite them getting significantly more calories, they lost more body fat. How can you eat hundreds more calories a day and still lose 2 more pounds of straight body fat? By just bringing your protein levels down to recommended levels. Who hasn't fantasized about a diet that allows ingestion of excess calories that are burned off effortlessly by ramping up fat burning? The researchers conclude that, quote, even a quite modest protein restriction regimen may have significant clinical benefits, unquote. A similar study found that even less protein restriction, taking men down to 73 grams a day, resulted in a 6-fold increase in FGF21 within a single week, accompanied by a significant increase in insulin sensitivity. The researchers conclude that, quote-unquote, dietary protein dilution promotes metabolic health in humans. Switching men and women from a high-protein diet of 138 grams per day down to a more than adequate 67 grams also multiplied FGF21 levels in the blood 6-fold, but within just 4 days. FGF21 may also explain the mounting evidence suggesting that a lower protein intake is associated with increased health and survival. Interestingly, both studies were feeding people about 9% of calories from protein, which is what the Okinawans were getting when they were among the longest-living populations in the world. However, not all proteins are the same. Animal protein versus plant protein. Some proteins may be more important to restrict than others. FGF21 is considered to be the most important mediator of the metabolic health benefits of restricting the amino acid methionine. As we know, amino acids are the building blocks of proteins. There are about 20 different kinds of them, similar to the numbers of the letters in the alphabet. Just as different sentences can be made from different combinations of letters, different proteins are made from stringing together different sequences of the various amino acids. Since methionine is one such amino acid found predominantly in animal proteins, we could potentially boost FGF21 levels by lowering methionine intake even without changing overall protein consumption, just by switching from animal to plant sources. Legumes, beans, split peas, chickpeas, and lentils deliver as much as 5 to 10 times less methionine than meat. You can check out the chart in the accompanying PDF. FGF21 has been proposed as an explanation for the protection from cancer, autoimmune diseases, obesity, and diabetes afforded by vegan diets. Maybe that's one of the reasons plant-based interventions have yielded such extraordinary results. Take Dr. Esselstyn's work, for example, suggesting that heart disease, our number one killer, can largely be halted or reversed, and risk for heart attack almost eliminated with the help of a whole-food, low-fat, plant-based diet. This benefit cannot be attributed solely to cholesterol reduction, as we now have powerful drugs that can force cholesterol levels as low as healthy eating can, but the pills appear to have far less effect. So maybe it's not just the fat and cholesterol, but the quantity and quality of protein playing a role. Harvard School of Public Health researchers proposed the quote-unquote protein package explanation for why plant protein sources are preferable to animal protein sources. Food, after all, is a package deal, so why get your protein prepackaged with saturated fat and cholesterol when you can get it with fiber and phytonutrients instead? But FGF21 presents a reason why the plant protein itself might be healthier. The theory was first proposed in 2015 but the first testing of vegan FGF21 levels wasn't published until 2019. FGF21 levels were found to be markedly higher in those eating plant-based. To prove cause and effect, omnivores were switched to a vegetarian diet, and the FGF21 levels in their blood shot up by more than 200% after just 4 days free of meat. The bottom line, a major review out of NIH's National Institute on Aging and the USC Longevity Institute, published on the clinical applications of fasting, concluded that, quote, various fasting approaches are likely to have limited efficacy, particularly on aging and conditions other than obesity, unless combined with high-nourishment diets such as the moderate calorie intake and mostly plant-based Mediterranean or Okinawan low-protein diets, unquote. The researchers specified that by low protein, they meant 0.8 grams of protein per kilogram of body weight, which is rather the recommended daily intake. How to lower IGF-1 with diet. In mice, protein restriction not only increases lifespan, but reduces frailty and improves physical performance later in life. FGF21 is suspected to mediate these benefits because all the anti-aging effects of protein restriction disappear in mice engineered unable to express FGF21. In people, other aging pathways may be involved. Diets with excess protein may be associated with increased oxidative stress and inflammation, as well as lower levels of NAD, which is critical for sirtuin function. Reducing protein intake can also reduce blood levels of IGF-1. Low IGF-1 levels predict survival in people with exceptional longevity. Remember from earlier how age-related pathologies like cancer were practically absent in those born with lifelong low IGF-1? IGF-1 appears to mediate the benefits of fasting for cancer, and its reduction with fasting is what causes the differential protection of normal cells and cancer cells, improving chemo's ability to kill cancer cells but spare normal cells. We know this because restoration of IGF-1 was sufficient to reverse fasting's protective effects. Starved cancer cells are more vulnerable to chemo in vitro, but this effect vanishes if the diminished IGF-1 is added back to the petri dish. A few days of fasting can cut IGF-1 levels in half, but that's largely because you're cutting your protein intake. Key determinant of circulating IGF-1 levels in humans is protein, particularly animal protein. Women and men eating strictly plant-based diets have significantly lower IGF-1 levels compared to those eating typical diets, including those who are comparatively slim, like long-distance endurance runners. It's not because they're eating fewer calories, because when it comes to lower IGF-1 levels, those eating plant-based also beat out cronies, the members of the Calorie Restriction Society, intentionally eating even fewer calories in an attempt to live longer, whom I mentioned earlier. In mice, caloric restriction alone lowers IGF-1, but people require protein restriction. The IGF-1 levels of practitioners of serious long-term caloric restriction remain elevated. As I noted before, the reason we suspect it's the protein is because if you take such practitioners and have them cut down their protein intake from 1.6 grams per kilogram down to 0.95 grams per kilogram a day, IGF-1 levels drop more than 20% within 3 weeks. IGF-1 is presented as a reason reduced protein intake may represent an important component of anti-aging and anti-cancer diets. A sidebar: potential downside of IGF-1 lowering. For at least 20 years, whole food plant-based diets have been advocated for slowing the human aging process by way of lowering IGF-1. IGF-1 also appears causally linked to cancer, heart disease, diabetes, and osteoarthritis, so it may help account for a panoply of plant-based perks. Those born with a lower lifetime IGF-1 also have enhanced cognitive performance. However, as I detail in c.nf/IGF-1BP, which is IGF just the numeral 1, BP, there may be a downside of IGF-1 lowering among those with high blood pressure. So those cutting down on animal protein should be particularly mindful of their blood pressure by reducing processed foods and added salt, while ensuring an ample supply of potassium-rich foods such as beans, sweet potatoes, and dark green leafy vegetables. Protein restriction. Evidence that protein restriction extends lifespan actually predates the evidence from studies using caloric restriction. Data on the relative importance of protein versus caloric restriction are mixed, but a comprehensive comparative meta-analysis of dietary restriction of more than 100 studies across dozens of species found that when it comes to life extension, protein reduction was more important. Sometimes it's hard to tease out, though. For example, when studies found that mice restricted to 70% of what they'd normally eat live longer, This may be chalked up to caloric restriction, even though protein was cut by the same amount. On the other hand, quote-unquote protein restriction studies in which mice are given all-they-can-eat low-protein chow may fail to show benefits because the mice eat more food to compensate, so they don't end up cutting their protein after all. The most impressive study to date tried to control for these factors by randomizing nearly 1,000 mice to one of 21 different diets systematically differing in protein, carbohydrate, fat, and calorie content. They found that the diets with the lowest protein to carbohydrate ratios yielded the longest maximum lifespans independent of calories. Markers of late-life health, including improved blood pressure, cholesterol, mitochondrial function, insulin sensitivity, and immune function, were also best on the low-protein diets and worst on the high-protein or high-fat diets. Low-protein, high-carbohydrate diets are able to generate the metabolic and immunity benefits of up to 40% caloric restriction without restricting calories at all. As the protein levels dropped, average lifespan increased from about 95 weeks to 125 weeks, an approximate 30% increase in lifespan even at the same caloric intake. The restriction of protein, not calories, was found to be driving the survival effect. In fact, researchers discovered that only restricting calories appeared to shorten lifespans. How can we square this with past studies with the same mouse strain that found the opposite? The new 25 Diets mega study used a novel method for restricting calories. The researchers designed all the diets ad libitum. How can you restrict calories if animals can eat all they want? The calorie restriction diet was bulked up with indigestible cellulose, basically sawdust, such that even when the mice gorged themselves, they would still be left with a 30% calorie deficit. Yet, despite the caloric restriction, they lived shorter, not longer lives. How do we explain same calories, different effects? Maybe the customary caloric restriction effect is really more of an intermittent fasting effect. Unlike the cellulose dilution diet, where the mice can eat anytime they want, if you just underfeed mice by giving them a fraction of what they'd normally eat, then once they finish their daily ration, they're effectively fasting until the next day. Might the conventional benefits instead be due to hunger signal pathways in the brain you might get from dietary restriction, but perhaps not from dietary dilution? Or maybe traditional caloric restriction cuts protein too, and that's the real driver of longevity? One potential caveat that arose from these series of experiments involves the quote-unquote protein leverage effect. On low-protein diets, the mice tended to overeat to try to compensate, so they were in effect eating more calories and still living longer. Obesity was prevented by feeding them high-fiber diets, but you can imagine how you wouldn't be doing your body any favors if your idea of a low-protein diet is one filled with ultra-processed junk like Snackwell's cookies. Indeed, low-protein longevity is undercut in mice-fed diets high in refined carbs. In humans, any negative effects of protein leverage may be countered by eating whole plant-based food. Animal protein versus plant protein. The optimal ratio of protein to carbohydrates across species for lifespan appears to be about 1 to 10, which is remarkably similar to the Okinawan ratio. The typical Okinawan diet was 9% protein and 85% carbohydrates, mostly from sweet potatoes, if you remember. Before they westernized their diets, they had among the highest number of centenarians in the world, with 80% lower rates of common cancers and 5 times lower mortality rates from a variety of age-related diseases in general. Some have suggested this was due to their relative caloric restriction, consuming about 20% fewer net calories than Americans, but they were also consuming about 50% less protein. In animal studies, the shortest lifespans were among those fed high-protein diets. This is consistent with a meta-analysis of prospective human cohort studies showing that higher total protein intake is associated with higher all-cause mortality rates. But that's because most protein eaten in the Western world comes from animal sources. The higher the animal protein intake, the higher the mortality rates, whereas the higher the plant protein intake, the lower the mortality rate. There is some evidence that those over 65 could benefit from slightly higher protein intakes. For example, 1 gram per kilogram of body weight instead of 0.8 grams per kilogram, which is still less than what most older Americans get. However, longevity experts suggest that this should be from plant-based sources to prevent excess IGF-1 activation. As I mentioned, The NIH AARP study, based on more than 6 million person-years of observation, found that swapping just 3% of calories from animal protein to plant protein was associated with a 10% decreased overall mortality in both men and women. Not all such studies showed this effect, but a meta-analysis of 32 such prospective cohort studies following people for up to 32 years found that overall, as little as a 3% increase in plant protein was associated with a significantly lower risk of dying from all causes put together. Significant improvements in health span appear to be achievable by even just a 1% animal-to-plant swap. A study of unhealthy aging used a quote-unquote deficit accumulation index, tracking more than 50 different functional impairments, measures of self-reported health and vitality, mental health indicators, chronic diseases, and needs of health services. Those who increased their plant protein by even 1% at the expense of animal protein, a swap of only about 5 grams a day, accumulated significantly fewer deficits over a period of 8 years. In the Women's Health Initiative, which followed 100,000 older women for 18 years, a 5% animal-to-plant protein swap was associated with about a 20% drop in the risk of dying from perhaps the biggest deficit of all, dementia. One study even found that swapping out a single serving a week of unhealthy protein sources like eggs for a healthy source like nuts or whole grains would hypothetically extend your lifespan. A 2022 meta-analysis on plant versus animal protein substitutions concluded their findings suggested, quote, introducing plant protein-rich sources to replace animal proteins to prevent aging-related diseases and promote longevity and healthy aging, unquote. Even more distinct than the caloric or protein restriction in the Okinawan Japanese was the skew towards plant sources. Animal products constituted less than 1% of their traditional diet, the equivalent of 1 serving of fish a week, other meats once a month, 1 egg about every 2 months, and practically no dairy. As we've discussed, the only formally studied population with a longer life expectancy didn't need a 99% meat-free diet, but rather a 100% meat-free, the California Adventist vegetarians, even though they were eating 30% above the RDA for protein. As a review on the impact of protein intake on longevity concluded, the protein source may be more important than the overall level of protein intake, though at high enough protein intake, IGF-1 levels may not drop even with a switch to mostly plant-based sources. What about randomizing people to a switch from animal to plant sources of protein and also a drop in overall protein intake? 16 weeks later, the lower protein plant-based group lost about 10 pounds of straight body fat, including hundreds of cubic centimeters of visceral fat, the dangerous deep belly fat, and experienced a significant decrease in insulin resistance. In Aging Research Reviews, this study was characterized as suggesting that a decrease in animal protein, quote, may be pivotal in improving metabolic health and aging, unquote. But given the concordant drop in animal fat as well, it's hard to tease out the primary driver of metabolic improvements. A sidebar: cancer restriction via protein restriction. T. Colin Campbell and colleagues showed nearly a half a century ago that rats on a 5% casein or milk protein diet developed 75% fewer precancerous lesions in response to a carcinogen compared to rats fed a 20% casein diet. Protein reduction can extend the lifespan of mice by about 30%, but cancer accounts for more than 90% of deaths of common inbred strains of laboratory mice. Given the outsized impact of protein reduction on cancer, we wouldn't expect the same life extension in people who die more often from heart disease. Human cancers show a similar response when transplanted into mice fed different diets. Human breast and prostate tumors show a 56 to 70% reduction in cancer growth rates in mice switched from 21% of calories from protein down to 7%. Even at the higher protein intake, just switching from animal proteins to plant protein can decrease tumor weights by 37%, though at the low protein intake, source didn't seem to matter. The decrease in tumor size from protein reduction was presumed to be due to a drop in cancer growth fueled by IGF-1, but low-protein diets were also found to stimulate the targeted killing of cancer cells by the immune system, increasing tumor infiltration by lymphocytes and enhancing the quote-unquote tumoricidal capacity of macrophages. Low-protein diets can also cause shrinkage of tumors in immune-deficient mice, suggesting it's a combination of factors. Even just limiting a single amino acid, methionine, can also slow the growth of cancerous tumors. Methionine restriction. Just as many of the benefits of dietary restriction can be replicated simply by restricting protein, most of the benefits of protein restriction may be due to the reduction of just a few of the amino acids that make up proteins, for example, methionine. Methionine is the only amino acid that strongly correlates with maximum lifespan across mammals, such that the more methionine in body tissues, the shorter the animals live, with an R of negative 0.96 for the stat nerds out there. The hearts of guinea pigs have about 40% more methionine than the hearts of rabbits, which can live about 40% longer. Mice have threefold higher methionine levels than naked mole rats, which can live 7 times longer. To prove cause and effect, you'd have to show that lowering methionine levels actually prolongs lifespan, and indeed, methionine restriction does just that. Simply restricting that one amino acid can increase the maximum lifespan of rats by up to 44%. More than one tends to see with caloric restriction. Methionine restriction also prolongs the maximum lifespan of mice, as well as improving stress resistance, decreasing visceral fat, and slowing aging of the eyes and immune system. The exact mechanism by which reducing dietary methionine leads to slower aging are not known, but methionine restriction boosts FGF21, induces autophagy, and reduces inflammation and IGF-1. The IGF-1 pathway may be critical, as mice with growth hormone signaling defects don't respond to methionine restriction, but there are other possibilities. In studies in which animals are fed excess amounts of different amino acids, methionine has consistently been found to be the single most toxic one. And this may be because methionine has a pro-oxidant effect. Supplementing rodent diets with extra methionine results in a spike in oxidative stress markers in their blood and a depletion of tissue antioxidants. Conversely, reducing methionine intake profoundly reduces mitochondrial free radical generation and oxidative damage to mitochondrial DNA, consistent with the mitochondrial theory of aging, the only amino acid ever shown to do so. Even restricting every other amino acid except methionine fails to reproduce this effect. Of all the amino acids, methionine is also one of the most vulnerable to oxidation. When it becomes oxidized while incorporated into a protein, that may lead to a loss of protein function. Thankfully, there's an enzyme, methionine sulfoxide reductase, that repairs this damage to protect cells against methionine-related oxidative damage. Genetically engineering animals to overexpress this methionine detox enzyme alone was shown to markedly extend longevity. Mild restriction of protein synthesis has been shown to rejuvenate senescent cells, enabling the so-called zombie cells to start growing again. This was demonstrated in vitro using a drug called cyclohexamide, which blocks the final translation step of protein formation. The researchers conclude, quote, "It is desirable to find a substitute for cyclohexamide to exert a holistic health-promoting effect to reduce excess and unnecessary protein synthesis," unquote. The same effect may be had by methionine restriction because methionine acts as the starting code for the translation of most proteins. Indeed, reducing the methionine concentration in a cell culture medium can result in a 60 to 75% increase in the replicative lifespan of human cells. The Hayflick limit, the number of times a cell can double before becoming senescent. Methionine-restricted cells are also significantly better at robustly resisting various stressors, including heat, radiation, carcinogens, and free radicals. How to lower methionine intake. Pharmaceutical companies are fighting to become the first to come out with a drug that decreases methionine levels, methionine-munching enzymes to give to patients with advanced cancer, for example. But since methionine is sourced mainly from food, a better strategy may be to lower methionine levels by lowering methionine intake. There are 3 ways to accomplish this. First is caloric restriction. By decreasing your intake of food in general, you reduce your intake of methionine. The purported pro-longevity benefits of alternate-day fasting, for instance, have been ascribed to the periodic depletion of the quote-unquote pro-aging amino acid methionine. Second, since methionine is in protein, instead of reducing food intake across the board, you could just cut down on protein. Simply reducing protein intake from present excessive levels down to recommended intake is expected to offer a large potential for health benefit. Third, even keeping portions and protein consumption the same, methionine restriction could be accomplished by switching from animal to plant protein sources, which tend to be relatively low in methionine. To achieve methionine restriction, a review on the impact of dietary protein intake on health and longevity concluded that individuals may need to, quote, eat less animal-based food, unquote. Termed the Hoffman effect, one of the universal hallmarks of cancer is, quote-unquote, methionine addiction. The methionine dependency of cancer cells has led to attempts to feed cancer patients a methionine-free, quote-unquote, amino acid-modified medicinal food powder, made mostly out of corn syrup, oil, and all the other amino acids. It's meant to crowd out methionine sources in the daily diet. The problem is that it's considered, quote-unquote, not palatable, so few people stick with it. Failed compliance with these oily corn syrup concoctions has led researchers to conclude that it is, quote, necessary to develop palatable foods in which methionine has been selectively removed, unquote. We already have them. They're called fruits and vegetables. Where is methionine found? Plant-based diets may, quote-unquote, make methionine restriction feasible as a life extension strategy. In the attached PDF, you'll find a graph comparing bioavailable methionine levels in common representative plant and animal foods. As you can see, fish is the worst, averaging 605, then poultry at 489. Much better would be eggs at 235, red meat 219, dairy 127. But the only ones falling under 100 are the beans at 54, nuts 31, greens 26, vegetables 14, fruits 7. As you can see, fish and poultry tend to have the highest levels of methionine. I used canned tuna as a representative fish, but 100 calories of fish such as haddock, halibut, or roughy can deliver even worse levels up to 709 milligrams. The lowest seafood levels are found in oysters, which average as low as 92. For poultry, I graphed grilled chicken breast, though roasted chicken breast can reach 587. Dairy, red meat, and eggs have less. I used hard-boiled eggs, but a whites-only omelet could top the charts at 714. I used ground beef as the representative red meat, but pork and lamb can go as high as 509 and 564, respectively, though blood sausage dips as low as 49. I used milk for dairy in the graph, though a dairy product like butter has nearly none since it's almost all fat. In contrast, high-protein dairy foods like cottage cheese can go as high as 42. The lowest methionine foods tend to be fruits, nuts, veggies, grains, and beans. I used canned chickpeas, but all the other beans have similar amounts, even the quote-unquote methionine-rich legume, the kidney bean, at 65. Only when plant protein is concentrated into a food like tofu can you get up around 114. For grains, I use whole wheat bread, but teff, the most methionine-rich grain, has 99, followed by quinoa at 64. For nuts, I used mixed nuts. Most nuts are similar, with the exception of Brazil nuts at 136. Hemp seeds are also high at 135. For vegetables, I used carrots. Spinach is surprisingly high at 184, but it's so low-calorie that you'd have to eat about 15 cups to get 100 calories. Kale is lower at 66 per 14 cups. I used bananas for fruit, but even oranges, the common fruit highest in methionine, average only 34. Achievable methionine restriction. The bottom line, a review on methionine restriction for life extension concluded, quote, in humans, methionine restriction may be achieved using a predominantly vegan diet, unquote. Even at the same protein intake, vegetarians may consume as much as 36% less methionine. Given the methionine concentration of eggs and dairy, though, only vegans end up with significantly lower methionine levels in their bloodstream. Although it may take an 80% reduction in methionine intake to maximize metabolic benefits in mice, a 40% methionine restriction was found sufficient to decrease mitochondrial free radical generation and oxidative damage to mitochondrial DNA. On average, vegans consume 47% less methionine than meat eaters. Perhaps this helps explain some of the health benefits attributed to plant-based diets. For example, short-term methionine deprivation can slim 60% of the fat mass off obese mice within 2 weeks, despite increased caloric intake and decreased physical activity, by apparently activating a quote-unquote feudal cycle of simultaneous fat formation and consumption. So maybe methionine reduction helps explain why vegans are 40 pounds lighter on average than those who eat conventional diets. Even vegans at the same weight as typical omnivores appear to have less than half the risk of diabetes, consistent with a 2022 analysis that followed about 15,000 U.S. adults for 17 years and found that those who ate the most methionine had more than twice the risk of dying from diabetes. On average, American women effectively consume twice as much methionine as they need, and American men 3 times as much. Given the cardiometabolic risk associated with higher intake, public health researchers suggest that the optimum intake may be down around the recommended intake. So just as I'm not advocating for a low-protein diet, but rather a diet with the recommended amount, one need not eat a low methionine diet, but rather just one without excess methionine. Given what we now know, simply decreasing intake to recommended levels, quote, has a great potential to lower tissue oxidative stress and to increase healthy lifespan in humans, unquote. A sidebar, cysteine and glycine. Much of the methionine we eat is converted into another amino acid within the body called cysteine. Given that the provision of extra cysteine to methionine-restricted animals reverses some of the benefit, cysteine might be responsible for some of methionine dirty work. While cysteine may be a partner in crime, the amino acid glycine is used by the body to aid in the clearance of methionine from the system. I go into detail on both in c.nf/cysteine-glycine. The bottom line is you can get more glycine in your bloodstream the same way you can get less methionine and cysteine by eating more plant-based. Branched-chain amino acids. The effects of protein restriction can't be completely replicated with methionine restriction alone, since the dietary restriction of all amino acids except methionine continues to have a range of beneficial effects, such as reduction in free radical production and oxidative DNA damage. Also to blame may be the 3 branched-chain amino acids, or BCAAs, isoleucine, leucine, and valine. In the 25 Diets mega-study, health and longevity consequences negatively correlated with BCAA levels in the blood, such that the lowest amounts were associated with the longest, healthiest lives. Interventional studies show that high BCAA diets shorten mouse lifespans, whereas BCAA restriction increases lifespan and delays age-related frailty in fruit flies and mice. The researchers suggest, quote, limiting dietary levels of BCAAs may be a key to a long and healthy life, unquote. This makes sense since BCAAs are potent activators of the engine of aging enzyme mTOR, which I talked about before. Reducing mTOR signaling is considered, quote-unquote, critical for improved health and lifespan, as mTOR suppression is a, quote-unquote, robust molecular transducer of diet-induced anti-aging signals. Lower BCAA intake may help explain not only Okinawan longevity, but why a disease like acne was rare or even non-existent, as pimples are considered a visual manifestation of elevated mTOR activity. Insight into potential cognitive effects comes from maple syrup urine disease. The irreversible breakdown of branched-chain amino acids is tightly regulated within the body. Babies born with a rare congenital defect in detoxifying BCAAs develop sweet-smelling urine and can go on to suffer encephalopathy, brain swelling, and death. The disease clearly shows that large excesses of BCAAs are hazardous to the brain, raising the question of whether milder elevations might also be neurotoxic. In a mouse model of Alzheimer's disease, high BCAA diets made cognitive performance worse, where low BCAA diets made it better. This is consistent with a Mendelian randomization analysis that found that people born with a genetic predisposition to higher isoleucine levels were significantly more likely to develop Alzheimer's disease. But a meta-analysis of 8 cohort studies found that higher levels of BCAAs, including isoleucine, were associated with a lower risk of dementia. The BCAA literature seems surprisingly rife with this kind of contradictory evidence, with studies suggesting that BCAAs have harmful, harmless, or helpful benefits on aging and age-related conditions. For example, there was an observational study that found that higher BCAA intakes were associated with a significantly lower all-cause mortality. With quote-unquote such levels of complexity, concluded a recent review on BCAAs and aging, quote, there is unlikely to be any unifying conclusion about overall benefits or harms of BCAAs in older people, unquote. However, at least when it comes to metabolic effects, we have human interventional trials to prove harms or benefits one way or another. BCAAs and insulin resistance. Insulin resistance is the cause of prediabetes and type 2 diabetes. Even in non-diabetics, insulin resistance and the elevated blood sugars that can result are associated with premature death based on meta-analyses of prospective cohort studies. For a backgrounder on what insulin resistance is and what it does, see my Low Insulin Index chapter in How Not to Diet. Insulin resistance, the inability of our body to sufficiently respond to the blood sugar-lowering hormone insulin, can be caused by the intake of saturated fat, check out c.nf/insulin, as well as the intake of branched-chain amino acids. Turns out that a BCAA breakdown product appears to stimulate fat uptake and accumulation inside the muscle cells, which interferes with insulin signaling. Reducing BCAA intake in obese mice reduced insulin resistance, caused dramatic fat loss even without a reduction in calories, and restored metabolic health, whereas a high BCAA diet induces mouse obesity. And people, a quote-unquote overwhelming number of studies have consistently shown that blood and urine levels of branched-chain amino acids are tied to insulin resistance. In fact, increased BCAA in the blood, dubbed the quote-unquote BCAA signature, is a hallmark of obesity and diabetes. This doesn't necessarily mean that decreasing intake of BCAAs will help, though, since there are other factors that influence levels in the blood. Yes, BCAAs can cause insulin resistance, but insulin resistance also seems to cause an increase in BCAA levels due to a reduction in BCAA breakdown, potentially leading to a positive feedback loop that can spiral out of control. The epidemiology is contradictory, though. The microbiome has even been thrown into the mix by a study of twin pairs showing that a fecal transplant from a heavier twin increases blood BCAA levels in mice more than a fecal transplant from the thinner twin. The proof is in the pudding, though. Just like you can make someone insulin resistant by infusing fat into their bloodstreams, you can do the same with infusing BCAAs. Just as a single dose of butter can cause insulin resistance within hours, so can downing a protein drink of straight whey and water. This may help explain the results of the study I detailed in the FGF21 section, in which protein intakes were dropped from typical American levels down to recommended levels. Not only did FGF21 double within about 6 weeks compared to the control group, but the drop in BCAA levels in the participants' blood was accompanied by a significant drop in blood sugars and pounds of fat loss despite averaging hundreds more calories a day. Given the restoration of metabolic health, demonstrated by decreasing consumption of branched-chain amino acids, leaders in the field have suggested the invention of pharmaceuticals to block BCAA absorption to quote-unquote promote metabolic health and treat diabetes and obesity without reducing caloric intake, unquote. Or we can just try to not eat so many branched-chain amino